Hi, everybody. We're in section 1.2, and again, I'm going to do the yellow problems, the 26, 28, and 30. Not because they're yellow, but because they're even numbers. So let me just copy this down too. So I'm going to turn this into a matrix. This is 2, 6, 16, 2, 6, 16, and there I have -2, -6, and -16, and now let me switch switch cameras so you can see it more better. Okay, so basically I'm going to take this is painfully obvious, what's going on here, but I'm going to do it anyway. Not that I'm in pain or anything. I'm gonna add row 1 plus row 2, and that's going to become my new row 2. And when I do that, so I have 2, 6, 16, and now I have 0, 0, 0. So basically, I turned this from 2 equations to 1 equation. And it's not really shocking. I mean, it's not hard to see that these 2 equations are really just the same equation. But let's just do a little more. I want to turn that 2 into a 1. So I'm going to take 1/2 of row 1 is going to become the new row 1. And now I have 1, 3, 8. 0, 0, 0. And by the way, I don't even need that 0 row anymore, at this point. But let's just remind ourselves that this represents the equation x plus 3y equals 8. Just again, we're going to see all these matrices, and the matrices don't have the x's and the y's, meaning that this first column is the x column, that's the y column, that's the constant column. And these matrices, don't have any x, y, whatever equal signs. There's no more stuff in them. But we have to always remember, always in math, when you see math symbols, you got to remember what they mean, because otherwise everything gets very theoretical, and it becomes a lot harder because you don't know what's going on over here. I'm going to let y be I'm going to let y be the parameter. So y is going to equal t. So I want to notice I don't just want to say infinite solutions. That's not good enough for us. We want to parametricize this. So we're going to so x is going to be 8. Well, I think it's pretty clear. X is going to be 8 minus 3t. Basically, I'm just solving for x in this equation. Eventually, I'm going to stop writing this stuff over here, and we'll look at the matrix. We'll just remember what it means. As soon as I saw this matrix 1, 3, 8, I knew 8 minus 3t, and I knew that this column was going to be my t column. And that's going to be my x column. That's going to be because the constant. So there you go. Anyways, that's our solution. So you can write the solution. I'm going to show you a couple of ways you can write the solution. Anyway, you can write it as 8 minus 3t, comma t, or you could write it. Or now I can't. Now in the past I factored out the t, but I can't do that. But I could write it as follows. I could write it. I can write the solution set as 8, 0 plus -3t, t. Or I can write it this way: 8, 0 plus t times -3, 1. These are just all different ways of writing the same thing. I can also write it. A lot of times I like to write these as column vectors. So I write it this way. I write it again. I'm just showing you different ways of writing the same thing. I write 8, 0 plus t times -3, 1. And again, this is nothing big. I'm just showing you different ways of expressing the same answer. This, and this all mean the same thing. I could have written it this way also. I could have written it this way. I could have written 8 minus 3t, and then t. I could have written the solution. There's this, and this, and just all different ways of expressing the solution set. Nothing, no actual method. I forgot to write it. This is 1.2, and this was number 26. Okay, and that's after this one. Let's go to let's go to the next problem. Oh, where'd it go? There it is. 28. All right, so I'm going to I'm just going to copy down the column here. And again, this is 1.2, number 28. I'm going to jot that down. 1.2, number 28. And I'm just going to copy down the numbers to put in the matrix. So it's 2, -1, -0.1. So we have 2, -1, -0.1. And then here we have, underneath it, we have 3, 2, 1.6. 3, 2, 1.6. Okay. I am going to now stop the share so you can see my paper. Now, basically, again, I want to turn this lower left into a 0. I want to turn that lower left number to 0. And I'm going to have this in that reduced, row echelon form. We call this Gaussian elimination, Gauss, whatever. Anyway, names are names. So what I want to do, I want to turn the top right number, the top left number, I want to turn that into 1, and the bottom number I want to turn into a 0. So I have a thing. I don't know if I mentioned this class, but I have an analogy. I don't know if I ever mentioned it in our class. I'm allergic to 2 allergies actually. I'm allergic to fractions and decimals. So I would like what I want to do here is I'm gonna let me show you what I'm gonna do. I'm going to, and again, you don't have to do what I'm doing. You could do it. You could just divide the first row by 2 and turn that into 1 and go on from there. There's no reason you can't do that. It's absolutely acceptable. That'll actually work, and you'll get the right answer. It's gonna be beautiful. I just have this thing. I don't know. Fractions and decimals bother me, so I'm just gonna do something a little. I'm going to switch row 1 and row 2. And again, I'm not saying you have to do this. I'm not saying this way is better. It's just how I see what to do. So now we have 3, 2, and 1.6. And here we have 2, -1, and -0.1. And now I'm going to add negative row 2 onto row 1, and that's going to become a new row 1. So, and now I have 1, 3, and let's see, that's 1.7. Because I added -1 onto 2, I got 3. I added -0.1 onto 1.6, and 1.7. And now down here I have 2, -1, and 1.6. And now I have my 1 that way. So I have a 1 here, and I don't have any more. As it is, I have fractions and decimals and things. It's annoying to me, but what can I do? Anyway, now I'm gonna go do my normal process. I'm gonna subtract 2 of row 1 from row 2. So -2 row 1 plus row 2, and that's gonna become the new row 2. So again, so only row 2 is changing to something new, which means I just straight copy the other row, but all the other rows. In this case, only one of them. So 1, 3, 1.7, and I don't know why the spacing is the way I am. I can tell you. That's going to be 0. -6 plus -1 is -7, and -3.4 and 1.6. So that's interesting. What's 3? Is that 1 point? Is that -1.8? Oh, they're just -1. Hold on a second. I'm really bad at subtraction. 3 point. Let's think for a second here. I'm subtracting 2, subtracting what's 3.4 minus 3.4, and that's 1.6. 6. Yeah. That's what happened to become 1? Oh, that came at 1.6 because. Hold on a second. Let me just make sure I didn't screw it. Yeah, yeah. Hi, everybody. Are we rolling? Yeah. Yeah, I just realized I copied something wrong. This 1.6, I guess I'm just looking at the wrong place. This 1.6 should really be a negative 0.1. That's so that should be negative 0.1. I meant to copy this number over here. Instead, I just literally just copied the wrong number. And that's the thing, by the way, when you deal with matrices, as you're going to see, there's like a billion different places where you can make a mistake. But what's nice about this is that if I add negative 3.4 onto negative 0.1, I get negative 3.5, which is nice because it's a multiple of 7. So I'm going to divide negative 1/7 times row 2 is going to become my new row 2. And now I have, let's see, 1, 3, 1.7, and here I have 0, 1, and that's going to be a negative, that's going to be 0.5. And now I am pretty much set. This represents, again, the two equations. This represents y equals 0.5. So we have our y solution. Now I have to take this 0.5, plug it into here, and I get, which tells me that 1x, this basically tells me here that 1x plus 3 times 0.5 equals 1.7, and that only happens if x equals 0.2. So my solution set is going to be, my solution set is right up here, is going to be 0.2 comma 0.5, and that's my solution set. So that worked out nicely, and we could again check the answers. I'll let you do that as an exercise, but go back to the original equations, put in x equals 0.2, y equals 0.5, and it will work. Okay, next. I really want to get to the third problem. That's what I really should be for. Okay, so okay, number 30. Now, number 30. I don't know if any of you are really sharp, but some of you may have noticed in number 30 that there are 3 equations. There's 2 variables, but 3 equations. And that's like a lot of equations. Now, that doesn't necessarily mean anything because sometimes when you reduce, sometimes, what I'm trying to say is that sometimes equations get reduced down. Let me give you an example. Before I do number 30, suppose I had here a system of equations. I have, I'm just making this up. X plus y equals 1. 5x minus 2y equals 17. And then I have a third equation. 2x plus 2y equals 2. Well, on the surface, this looks like 3 equations. But really, it's just 2 equations because the top one and the bottom one is really the same thing. They're really duplicates of each other. So this really this is 2 equations, not 1 equation. You see what I'm saying? So just because it looks like the 3 equations. Now, I'm not saying this could be the case with problem number 30, but that could be the case. So we have to and let's say there are 3 lines. Let's say each of these represents a line. The equation is as written here. And 3 lines could intersect in one place. That could be a solution. 3 lines might not intersect. They might be parallel. They might be whatever, you know. So again, we can't just say, oh, there's 3 equations, 2 variables. That's it, you know. Oh, that's it. Go home. Nothing to talk about. We can't just do that. So let me get another piece of paper, and let's actually do this problem. So now let's go to 1.2 number 30. Excuse me. 1.2 number 30. Okay, you know what I'm gonna do? I just thought of a great, just thought of a great idea. Here we go. Okay, so let's do it here. So I'm gonna write this down as a matrix. And that's 1, 2, 0, 1, 2, 0, and 1, 1, 6, and 3, -2, 8. 3, -2, 8, and I ate and I left no crumbs. That's what Gen Z people say. Don't even ask, I have no idea what that means, but that's what Gen Z people say. Okay. I think. So let me I wanna get rid of this screen and go onto my paper so you can see better. Okay, so it seems pretty clear what I'm gonna do here. I want to get all zeros down this first column. That's the again, we're trying to make that sort of triangular um array. So which means ultimately I'm gonna want zeros when I'm dealing with a 3 by 3 matrix. I just show what I mean. These numbers are not necessarily accurate numbers. I'm writing here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I eventually want to do a bunch of row operations to make it look like this: 1, 0, 0, then 5, 22, whatever these numbers wind up being. And then 3, and then 7, and then 14 and something like that. But then, because I want to turn that into a 1, and then ultimately I want to make it even better. I want to make it 1, 5, 22, 0, 1, 7, and then I left out my constants. Sorry about that. Whatever, you get my point. I want that little triangle. I'm spending too much time saying something else. I want to get that little triangle with zeros in the bottom. This kind of a triangle thing with zeros in the bottom. So again, I know that's not the way you solve systems of equations in high school, but that is how we're doing it in matrices, and that's going to be very, very. This method is actually going to be very, very useful. It's used a lot in linear algebra, and we're going to see more and more. We're going to get more and more insights into systems of equations in this course, and we're going to see why this elimination, this triangular kind of method, is so valuable. But anyway, let's just do it. So I want to subtract row 1 from row 2. That's going to become a new row 2. And I want to subtract thrice row 1 from row 3. That's going to become a new row 3. Now, as I said before, I said it before, I'm going to say it again. It's a little dangerous what I'm doing here, because every time you do an operation, you should change and rewrite the matrix. Because sometimes after the first operation, it's going to change the matrix, and then that's going to affect what is row 1, row 3. The reason I can get away with this is because after the first operation, the only thing that changes is row 2. Row 1 is used to change row 2, but row 1 itself doesn't change. Only row 2 is changing, becomes a new row 2. And the second operation doesn't have any row 2. So even though row 2 got changed by the first operation, it doesn't pop up in the second operation. It's like, who cares? So I can get away with being a little, just for the sake of space, I can get away with this, even though you got to be careful about doing this. So, but I am a trained professional, so I can do this. And so can you. So that's going to become 0. And ultimately, that's going to become 0. So let's just get my zeros. Anyway, so -1, -2, that becomes a -1. And now it's subtracting 0. That's nice. That's good. 6. And this is going to stay in 8. That's nice. Second. Let me just close this. Okay, so and now finally, let's see. -3 times 2 is -6, plus that becomes -8. All right. And I guess I'm going to divide. I'm going to divide. Well, I can see right now. By the way, I can see it already. that we got problems. I can see already we got problems. I can see right away that the second row tells me that y is equal to -6. And the bottom row tells me that y is equal to -1. I can see that already. You know, but let's do this a little more official. I'm going to first. I'm gonna multiply. I'm gonna let negative row 2 become the new row 2. And then I'm going to subtract. I'm going to add 8 row. I'm going to add 8 row 2 to row 3, and that's going to be my new row 3. So I ate and I left no crumbs, which again is a Gen Z thing. So now my matrix is 1, 2, 0, 0, 1, 6, and 0, 0, and 48 plus 8 is what's 40, 56. Now the bottom row, what does the bottom row mean? 0, 0, and 56. Well, that tells me that 0x plus 0y equals 56. That just doesn't make sense. This bottom row just tells me that 0 equals 56, which is of course a contradiction, which means no solution. And that's the answer to this. That's the answer to number 30. No solution. I want to graph this. I'll just show you what this looks like. It's, it's gonna. So let's see. I'm gonna share my screen. Let's share my screen. And okay, what just happened? Oh, it is my screen. And now I'm also gonna go to Desmos so I can. Oh, do a screen share. Okay, where is it? Okay, it's coming. It's coming. Okay, it's coming. All right, and there's Desmos right there. All right, so the equations were x plus 2y equals 0, x plus 2y equals 0. That's weird, okay? Not sure how that happened, but plus 2y equals 0. And then the other equation, is going to be x plus y equals 6, x plus y equals 6. And the last equation with the intercept right there. That's cute, the intersect. Okay. And now 12 comma -6. Right. Because you see if x is 12 and y is -6, that's going to be 0. And 12 minus 6 is 0. These go worse. Now, if the third line, which I'm going to graph now, goes through that point, then we have a solution. But we already know, we already showed algebraically that there is no solution. So I'm sure we're going to want to get in some kind of triangle thing. Let's just do it. 3x minus 2y equals 8. And there you go. So I have, so here's my situation. This is the situation now. So we don't have, even though we have, remember, as one of the primary, the cardinal rule of systems equations, is that even though 12 comma -6 satisfies the first two equations, and 4 comma 2 is going to satisfy the third and the I don't know which the second and third equation, and 2 comma -1 is going to satisfy the first and the third, but there's no one ordered pair. There's no one that satisfies all three equations. And in order to be a system for the solution, but for this, I'm sorry, in order to be a solution, I switched up the two words. I feel only one can now. I'm going to reverse that. In order to be a solution for the system, I need a solution that solves all three equations. I don't have that. I have a couple of almost guys, but I don't have any. Now, because there's other ways this could happen. I could have had. There are many ways you could have. I'm just take the share off here. Geometrically, there are many ways this could happen. You know, you can have. You can have. Well, you can have what we just showed. You could have three parallel lines. We could have had. We could have had two parallel lines cut by a transversal. So again, we have points that partially satisfy the thing. Here we have points that partially satisfy. Here we have nothing that satisfies it. You know, so there are a lot of. I'm trying to think of any other ways. I'm trying to think of all the ways I could draw this geometrically and have no solution. I think these are the only three I can think of offhand. Can we think of another way, a geometric way, how you can have? There's all you need. The only way that there is a solution is if you have all three going through the same point. Now, of course, you can have 1, 2, 3. So these two lines, so you have two lines on top of each other, and the third line, but that's to make it that point, we've got a solution. But you could have 1, 2, 3, all three lines on top of each other, which means infinite solutions across that whole line. There's a lot of, these are just all the various geometrical possibilities. But we've done the problem, and that's it. Oops, that's it for now. So we're gonna end this video, and we'll see you on the next one. Okay, bye everybody. Bye.